Imagine an object so powerful that once you cross a certain point, time slows, space collapses, and escape becomes impossible. No explosion, no warning, no second chance. Black holes are not cosmic vacuum cleaners. They are not portals, at least not yet. And they are not just objects in space. They are the ultimate limits of reality itself. Every law of physics we trust, every equation we rely on, every certainty we believe in breaks down at the edge of a black hole. If you fell into one, you wouldn't just disappear. You would experience the universe in a way no human ever could. And the strangest part? Black holes are not rare. They exist at the center of almost every galaxy, including our own. So the real question is not what black holes are. The real question is, what do they reveal about the true nature of the universe? In this video, you will discover what black holes really are, beyond science fiction, how they form from dying stars and warped space-time, what happens if you fall into one step by step, why time itself behaves differently near a black hole, what lies beyond the event horizon, and why black holes may hold the key to understanding reality itself. Welcome to Where the Light Ends, a place where space grows silent, light fades, and the universe begins to reveal its darkest secrets. A black hole is not a hole. It is not empty space. It is not a tunnel. And it is not a doorway by default. A black hole is matter compressed so densely that space-time itself collapses under its weight. To understand this, we need to rethink gravity. Gravity is not a force pulling objects together. According to Einstein's general relativity, gravity is the bending of space-time itself. Mass tells space-time how to curve. Space-time tells matter how to move. Under normal conditions, this curvature is gentle. Planets orbit stars. Stars orbit galaxies. But when an enormous amount of mass is squeezed into an incredibly small volume, space-time doesn't just bend, it collapses. That collapse creates a black hole. At its core lies something we cannot fully describe, a point of infinite density known as a singularity. At the singularity, density becomes infinite. Space and time lose their meaning. Our equations stop working. Physics, as we know it, ends. Surrounding the singularity is a boundary called the event horizon. This is the point of no return. Once anything, light, matter, information that crosses this boundary, it can never escape. Not because black holes suck things in, but because escape would require moving faster than light, and nothing in the universe can do that. From far away, a black hole looks calm, silent, invisible, almost peaceful. But as you approach the event horizon, something strange happens. Time begins to slow. To an outside observer, you would appear to move slower and slower until you seem completely frozen at the edge. You would never be seen crossing the event horizon. You would simply fade away. But from your own perspective, time would feel completely normal. You would cross the event horizon without noticing anything special. No wall, no explosion, no sudden darkness, just inevitability. Most black holes are born from death. When a massive star runs out of fuel, it can no longer resist gravity. The core collapses. If the mass is great enough, not even neutron pressure can stop it. The star implodes, and a black hole is born. These are called stellar mass black holes, but there is another kind. At the centers of galaxies lie supermassive black holes, millions to billions of times more massive than our sun. We still don't fully understand how they formed. Some theories suggest they grew from smaller black holes, they formed directly from collapsing gas clouds, or they emerged in the early universe itself. At the center of the Milky Way lies one of these giants, Sagittarius A, 4 million times the mass of the sun, quiet, invisible, patient. Black holes are not cosmic mistakes. They are natural consequences of the universe's laws. They shape galaxies. They influence star formation. They may preserve information in ways we don't yet understand. Some physicists believe black holes are laboratories for quantum gravity. the missing bridge between relativity and quantum mechanics. Others believe they may hint at deeper structures of reality, dimensions beyond our own, holographic universes, information encoded on cosmic boundaries. Black holes are not just objects in space, they are questions. As matter falls toward a black hole, it doesn't disappear quietly. It spirals. This creates what is known as an accretion disk, a swirling ring of superheated matter rotating at near-light speed. The friction inside this disk generates enormous energy. In fact, accretion disks around black holes are some of the brightest objects in the universe. Ironically, the darkest objects ever discovered are often surrounded by blinding light, X-rays, gamma rays, radiation powerful enough to outshine entire galaxies. So black holes are not invisible monsters. They announce themselves through the chaos they create. If you were unlucky enough to fall toward a black hole, gravity would not pull you evenly. Your feet would feel stronger gravity than your head. This difference stretches you, violently. This process is called spaghettification. Your body would elongate into a thin stream of atoms before reaching the singularity. Every molecule, every atom, every particle, pulled apart by tidal forces beyond imagination. For small black holes, this happens before you cross the event horizon. For supermassive black holes, however, you might cross the event horizon intact, alive, aware, unaware that escape is already impossible. Black holes reveal one of the most disturbing truths in physics. Time is not absolute. Near a black hole, time slows relative to the outside universe. This is not a theory. It has been measured. It has been confirmed. If you hovered near the event horizon and then returned to Earth, thousands of years could pass while only hours pass for you. You would witness the future of the universe unfold. This is gravitational time dilation, and it means something terrifying. Black holes allow one-way travel into the future, but never back. Once you cross the event horizon, space and time switch roles. Time no longer flows forward. It flows toward the singularity. You cannot stop. You cannot turn around. Reaching the singularity is as inevitable as reaching tomorrow. Inside a black hole, the concept of staying still no longer exists. Every possible path leads inward. Reality becomes directional. For decades, black holes were believed to last forever. Then Stephen Hawking changed everything. Using quantum mechanics, he showed that black holes are not perfectly black. At the edge of the event horizon, quantum fluctuations allow particles to escape. This creates Hawking radiation, extremely weak, almost impossible to detect. But over unimaginable timescales, black holes evaporate. They lose mass, they shrink, they fade. Eventually, after trillions upon trillions of years, a black hole can disappear completely. This raises a profound problem. What happens to the information that fell in? Physics says information cannot be destroyed. Black holes seem to erase it. This contradiction is called the black hole information paradox. It is one of the greatest unsolved problems in science. Some theories suggest information is stored on the event horizon. Reality behaves like a hologram. Space itself encodes information on its boundaries. If true, the universe may be far stranger than we imagine. Black holes are not just cosmic objects, they are boundaries. Beyond them, our understanding fails. They sit at the intersection of gravity, quantum mechanics, space, time. To understand black holes fully, we must rewrite physics itself, and that is why they matter. Because whatever lies beyond them defines the limits of reality. Imagine this. You are floating in space, no engine noise, no air, only silence. Ahead of you is a black hole, not a sphere, not a hole, just darkness. At first, nothing feels different. Your instruments work normally. Your heartbeat is steady. Time feels ordinary. But the universe around you has already changed. From far away, the black hole seems harmless. Gravity feels weak. But gravity doesn't pull evenly. It stretches. As you drift closer, space itself begins to curve beneath you. Light from distant stars bends around the black hole, forming a glowing ring. This is gravitational lensing. You are no longer seeing the universe as it truly is. You are seeing a distorted reality. Your clocks start to behave strangely. Seconds stretch. Movements feel normal to you, but to an outside observer. You are slowing down. Your radio signals grow weaker. Your voice deepens. Your image freezes. To the universe outside, you never cross the event horizon. You fade, you freeze, you disappear. But you feel none of this. There is no warning, no flash of light, no explosion, no sudden darkness. You cross the event horizon without noticing. At this moment, escape becomes impossible. Not because something grabs you, but because the future now points inward. Every possible path leads deeper. Inside the event horizon, space behaves like time. You cannot stop falling any more than you can stop tomorrow from arriving. Even light cannot remain still. The singularity is no longer a place. It is a moment, and that moment is unavoidable. Gravity increases dramatically. Your feet are pulled harder than your head. Your body stretches. Atoms separate. Molecules unravel. Structure dissolves. This is spaghettification. For supermassive black holes, this happens slowly, painfully slowly. For smaller black holes, it happens instantly. Light behind you speeds up. The universe outside accelerates. Stars age. Galaxies collide. The future unfolds in seconds. You could, in theory, witness the end of the universe before you reach the singularity. At the center lies something unknowable: infinite density, infinite curvature, no space, no time, no laws. Physics ends here. What happens next? Science has no answer. Your atoms are not destroyed. Your information may not be lost. Some theories suggest your data is smeared across the event horizon, encoded, preserved, transformed. You may not disappear. You may become part of the black hole itself. The true horror of falling into a black hole is not destruction. It is inevitability. Once crossed, nothing can change your fate. No decision, no force, no escape, only descent. Black holes are not just objects, they are messages. They tell us that reality has limits, and that we are standing dangerously close to them. Every successful theory in physics breaks down near a black hole. General relativity fails. Quantum mechanics disagrees. Space and time lose definition. At the singularity, our equations return impossible answers: infinity. And in physics, infinity means we don't understand something. Black holes expose the cracks in our understanding of the universe. One of the strangest ideas born from black hole physics is this: reality may be a hologram. According to the holographic principle, all the information inside a volume of space can be encoded on its surface, just like a black hole. This means our three-dimensional universe could be a projection of information written on a two-dimensional boundary. We may not live inside reality. We may live on its surface. Black holes reveal that time is not fundamental. It stretches, it bends, it breaks. Near a black hole, past and future blur. Inside one, time loses direction. Some physicists believe time emerges from deeper quantum processes, not the other way around. If true, then time is not the stage of reality. It is a side effect. If black holes evaporate, where does information go? Does the universe forget, or does it remember in ways we don't yet comprehend? The answer may determine whether reality is deterministic or fundamentally uncertain. Black holes are forcing us to redefine what existence even means. Science does not support the idea that black holes are portals, not yet. But theoretical solutions suggest strange possibilities. Wormholes, white holes, other regions of space-time, entirely new universes. These ideas remain speculative, but black holes are the only places where such ideas might be tested. Why the universe needs darkness. Without black holes, galaxies would not exist as they do. They anchor stars. They regulate growth. they sculpt cosmic structure. Darkness is not the enemy of light. It is its boundary, the final truth. Black holes teach us something deeply unsettling. The universe is not built for understanding. It is built for consistency. And when consistency fails, mystery remains. While researching black holes, I realized they are not just cosmic objects, but mirrors reflecting the limits of human understanding. What disturbed me the most was not their power, but their silence. They don't threaten, they simply exist. The idea that time can slow, break, or even lose meaning near a black hole completely changed how I think about reality. It made me question whether we truly experience the universe as it is, or only as our minds allow us to. Black holes remind us that knowledge has edges, and beyond those edges lies uncertainty. And maybe that uncertainty is not something to fear, but something that gives the universe its meaning. This is where the light ends. Thank you for watching. And remember, some questions are meant to remain unanswered.